Hello class, today's lecture is about extraction and sublimation. This is your TA, Hubert Fonseca, telling you to please read the textbook, section 9 and section 8.3 about extraction and sublimation correspondingly. So before we talk about the techniques that you'll be using in this laboratory, let's talk about the chemicals that you'll be trying to separate. So caffeine. Caffeine is a white crystalline solid when it's pure. It's bitter in taste, and you can find it in coffee, tea, and Coca-Cola. Interesting fact: on an average, Americans consume 150 milligrams of caffeine daily. I know that caffeine has it depends on the person's sensitivity to caffeine, but it has a high threshold, so you only need a little bit to feel the effects of it. Think about why we take caffeine. Well, it's probably because of our busy lives as chemists. Most researchers I know drink caffeine, but that's the important information for us as chemists is that caffeine is moderately soluble in room temperature water, but it's very soluble in boiling water. So you can think about your Gen Chem days. In low temperature, it's 2 grams per 100 milliliters of water, and in a high temperature, it's 66 grams per 100 milliliters of water. So the constant of the solubility constant changes with respect to temperature. But not just temperature depends or affects the solubility of caffeine, but also the solvent. It is very soluble in anorganic solvent like dichloromethane, which is a polar solvent. You can see the halogen here, chlorine. So right now you can be thinking, how can I separate caffeine if it's contaminated? You can think about, for example, crystallization, which was something to get that, which was a technique to separate a solid from a liquid. Here you can already start thinking, well, caffeine is a solid. How can I separate caffeine from other solids or perhaps from other liquids? Because that's our tasks as chemists. Besides caffeine, what else are in a tea bag, for example? Every time you put a tea bag in the boiling water cup, what are you doing? What is actually going on, right? Well, the caffeine is being dissolved in the hot boiling water, right? 66 grams per 100 milliliters of water. But not only is the caffeine being dissolved, also there's cellulose and there's tannins inside of that tea. So are these soluble in boiling water? Can you separate those in order to obtain pure caffeine? These are questions that concern us as chemists, and not only with caffeine, of course. You can all in your house you can see different chemicals that you would want to separate from your food, for example. So one of the things that you can find in a tea bag is cellulose, for example. Cellulose is a polysaccharide. Polysaccharides are made up of monosaccharides from you can remember, if you can remember biochemistry or biology, simple monosaccharides, for example glucose. They can look like this, or they can look like this. This oxygen here is this oxygen, and this tail is this tail, right? So you have a six-member ring, and it's a 6-carbon sugar, right? 1, 2, 3, 4, 5, 6. It's a hexose. We call these kinds of compounds hexose. Fructose being an isomer of glucose, and so on and so forth and so forth. However, the structure of cellulose is a polysaccharide, and so it's pretty much glucose, several monomers, several monosaccharides of glucose connected together, and this is not soluble in water. This is not soluble in water, so right now you can be thinking, okay, I can separate caffeine from cellulose through water, right? Because cellulose cannot dissolve in water, but caffeine can. So there's got to be a way, right? There's got to be a way to separate the two. The second thing that is in tea bags is tannin. Tannin is a polyphenolic compound. So it's a compound that has several phenol rings around it. This is a benzene ring, right? This is a benzene ring, but it's really a phenol because it has an OH attached to it, at least one, right? And it's connected through ester linkages. This is an ester, this is an ester, this is an ester. And if you hydrate it, you can separate this molecule, this tannin, into glucose. This is glucose, Remember the tail and the oxygen here, and the six-membered ring, um, six carbons, six-membered ring. That's glucose, and this is gallic acid. You can obtain this from the hydration. You basically put in an OH here, and you put in an H here. That's hydrolysis, right? But see, the problem is that gallic acid is not soluble in water. It's only partial. Well, it is, but it's only partially. So by adding a base such as sodium carbonate, you can convert this gallic acid into its salt, its sodium salt. If you read the book, which I advise to, they use, for example, calcium. So they make the calcium salt. And you generate carbonic acid, which then decomposes into water and carbon dioxide. The important part here is to be thinking, well, glucose is soluble in water, so I cannot separate caffeine and glucose just by just through water as a solvent. You can separate cellulose, but not glucose, not quite glucose. And even less gallic acid, because it's still partially soluble in water. And by adding that base, by deprotonating this hydroxide group, it is even more soluble in water. But you can use this as your advantage, because as we saw earlier, that tidbit of information that caffeine is actually soluble in dichloromethane. Are these compounds soluble in dichloromethane? We'll see right now. So to summarize, caffeine is soluble in hot water, as you can see when you dip that tea bag in hot water, but it's also very soluble in DCM, and we can use that as an advantage. Tannin, which is also in tea bags, tends to separate into glucose and gallic acid just by hydrolysis reaction. Both are water soluble, especially if you add that base. Cellulose is not water soluble, so we should not be that concerned for that compound too much, right? Again, here we have the three components. We have caffeine, we have cellulose, and we have tannin. Since cellulose is not water soluble, it's water insoluble, you can separate that by filtration, by simple filtration, and we'll see how easy it can be. We are interested in caffeine, and we know that it's hot water soluble, and it's very soluble in DCM. So first, since here we have a lot of impurities, we have a lot of stuff that we don't want, we know that it's hot water soluble. So the first step, think about what the first step should be to get caffeine out of the tea bag. Well, naturally you would boil the bag, right? You put it in a cup and try to boil out. You try to dissolve the caffeine in hot water, and as you do that, it'll come out. The tannin will come out, caffeine will come out, and cellulose should stay mostly there, but we're still going to apply filtration to make sure that none of the cellulose comes out. What else? These are the equipment that you will use. Make sure you have a general idea and a specific idea as we go through it, so that you can answer questions on the quiz and you can understand this procedure more correctly. Like I said, the first step is brewing the tea. You want to get that caffeine out of the tea bag and into the boiling water, the hot water. Caffeine and tannin from tea bag goes into a hot sodium carbonate solution. It works out to already have that base in there, so that as the tannin is coming out, it decomposes or it hydrolyzes into gallic acid and glucose, right? Cellulose remains insoluble. It remains mostly in the bag, but the next step would be to apply vacuum filtration to make sure that the cellulose will not carry out into our later steps, right? So you take a 250 milliliter beaker. You always, when you choose a beaker, you always try to take into account the volume that you're going to put it in. So if you're going to put 100 milliliters of water and you're going to boil it, it's a good idea to have 250 mLs. Water is sort of not too violent, but it's sort of violent, right? If you fill a pot up to the brim with boiling water, it will spill out and it'll make a mess, right? So just a tip when choosing beakers. And then you add 2 grams of sodium carbonate, and you fill it with 100 mLs of water. You mix and make the solution, and then put 5 tea bags, or as many bags as we tell you. And you have to know the approximate mass of the tea that is in there, so that then you can calculate your yield, which you would write in your notebook, in your lab notebook. You boil the water, you wait for the caffeine to come out into the solution, and if water vaporizes, you add more water, and you keep the water level between 75 and 100 mLs. Once we have the caffeine and tannin solution, you want to filtrate the solution to make sure that the cellulose does not accompany the solution. So you would perform vacuum filtration. You get one of these Erlenmeyer flasks with a vacuum adapter, or a vacuum adapter. You put a rubber adapter here, and then you would use a Buchner funnel, right? The Buchner funnel, of course, comes with the right size filter paper, and then you turn on the vacuum, and then you would likely want to wet a little bit the sides of the paper, and then you would dump the solution with the tea bags onto the Buchner funnel, and you press the tea bags on the Buchner funnel to drain the solution, so you can get the liquid out of the bags as much as you can. And of course, the cellulose should not carry onto the solution, because we don't want it, right? Now to the liquid extraction. So here you'll meet the separatory funnel, one of an organic chemist's best friends. You transfer all the brown solution of caffeine plus tannin from the vacuum filtration of the apparatus, from that Erlenmeyer, to the separator funnel. Before you do that, though, you make sure that this stopcock, that this lever, is set on the horizontal position or the vertical, depending on the separatory funnel, so that it doesn't come out, right? Even before you pour it in, you want to have a beaker like this, to make sure that even if it's broken, or if you forget, so that you don't spill your product and you mess it up, right? So the extraction. So this works on the basis of solubility, which in the end is in function of the polarity of your product, right? Like dissolves like, again. So the point here is that we're adding 10 mLs of DCM. Well, think about why we're adding DCM, right? We have that brown solution with caffeine and tannin. We know that caffeine dissolves in water, and tannin does too. Well, at this point, actually, it's gallic acid, right? Well, it's salt, sodium salt, and glucose, right? And all three things are soluble in water. But we also know that caffeine might be more soluble in DCM. In fact, it's very soluble in DCM. So by adding DCM, you can read about it in the textbook. The DCM will actually extract the caffeine out of the water that is dissolving the tannin components. And to ensure that you do that DCM actually takes out or extracts the caffeine, you add the DCM, and two layers will form. There will be a colorless, since caffeine is usually a white crystal. It does not. So you can already imagine that the DCM is taking out the caffeine from this brown solution, and it's coming onto here, and so it's colorless. And you can that way you can already know that this layer is going to be the one where caffeine is. And one way to do it is to cover this separatory funnel, and then shake gently. And the traditional motion that you do is like a back and forth, like rocking, with this end pointed away from you and from others, because generally pressure builds up, and you want to open it a little bit as this is pointing up and away from you, so that the accumulated pressure leaves the separatory funnel. But you also want to cover this side, of course, because the liquid, the layers are going to be pushed that way. So that's why you add a stopper here, right? And you put your hand on top of it to make sure that it doesn't come out. And then the brown filtrate, you would want to keep it in here, and you keep draining the DCM layer. And if you read the textbook, you'll see that it's important to do this several times, because instead of using 30 mLs of, this is very important, okay? Instead of using 30 mLs of DCM, you use 10 mLs of DCM 3 times, and you wash this, or you extract as much caffeine as you can from this brown filtrate. You're essentially washing this filtrate and getting it rid of the caffeine, which is the thing you want. And so every time you do that, you add 10 mLs of DCM, you get this separate layer, you stop it, you put the stopper, you shake gently, and again, you'll see once you put it in the ring clamp, you'll see that the two layers separate, and then you drain the DCM layer again, and this is what you keep accumulating. Be careful when draining the DCM layer. Every time, leave a little DCM layer in the separator funnel to make sure that the brown color filtrate doesn't come out and contaminate again your product, right? Also, when you open the separatory funnel, you have to make sure that you get rid of the stopper, because you essentially create a vacuum here every time you open and close the separatory funnel. So it will stop the liquid from coming down. So you have to make sure that you get rid of the stopper. Now, in a research lab, this next step is often very much needed and required. In this lab, not so much, especially if you did the extraction correctly. If you didn't do it correctly and you got some aqueous layer, and that's the way we call it, the DCM layer we call the organic layer, and the brown filter we call the aqueous layer, the one containing the water. It's usually the one that we don't want as organic chemists, right? But that colorless DCM solution with your caffeine, it might still contain very small molecular level quantities of the aqueous solution. So you add a little bit of drying agent. It could be magnesium sulfate, it could be sodium sulfate, and you do it by gravity filtration. You pour in the solution with magnesium sulfate in it, and the solution that you want will drop here, sometimes dropwise, sometimes very quickly, and the magnesium sulfate will accumulate here. It's very important to remove the drying agent so you can conduct a further reaction later, or whatever you might need with it, so that the drying agent does not interfere, right? And finally, we have sublimation. We often do not do this in organic chemistry labs. This is kind of like flexing, but it's still important to know, right? It's unconventional technique, but it's important to know. So you need a set of two beakers that satisfies the following condition. You have a small beaker, and you could put it in this large beaker, and the small beaker must hang right inside of the large beaker, so that there's a relevant gap, right? There's an important gap here. Do not fill the small beaker with ice yet, and you'll see why. So the large beaker will contain the DCM solution, and you're going to heat it up. You're going to heat it up, and the DCM will evaporate. It'll evaporate, and the large beaker now contains some white solid. That should be the caffeine. And then you wait until all the DCM vapor disappears. And then the small beaker, you fill it with ice, and you quickly but carefully drop the small beaker inside of the large beaker. You increase the heat, and you'll, as we'll see, there will be white solid that begins accumulating on the side of the small beaker. However, there is a problem, especially if you did not do the extraction correctly and you did not dry the solution. Because we're using a cold beaker, the small beaker that contains ice, The major problem in sublimation is moisture condensing outside the small beaker. If that happens, there's not much to do other than just watch that your sublimation step is not working. You will maybe try this several times and it won't work. To avoid the problem, make sure you remove any water from your system. And that's why also you need to add ice quickly and then put it into the big beaker quickly, because you'll see most of the time moisture will begin accumulating on the small beaker, dissolving again the caffeine, because caffeine is soluble in water, and you won't be able to get your pure compound, your pure caffeine, right, for your morning coffee. You must dry your DCM solution with anhydrous magnesium sulfate, again, that drying agent. If your ending solution contains aqueous brown droplets, and perform gravity filtration to get rid of the drying reagent. Avoid any moisture condensation outside of small beakers that contains ice. So again, you put the large beaker in high heat. In that large beaker, you wait until the DCM disappears, mostly, because DCM will interfere here with the small beaker as well. You fill the small beaker with ice, and you quickly drop inside the large beaker, and you'll see caffeine accumulating here. Now, I remember when I performed this experiment, and I realized that the best way to collect these caffeine crystals after the fact that we sublimate them, right? Because there was a solid, it's not quite touching the white solid. It evaporates, it sublimates, and then it comes back as a solid here. So in a way, it sublimates and it deposits on the small beaker. So once you remove the small beaker, you use a spatula and put it in waiting paper. You put it in waiting paper. You weight your product, and then you calculate the yield. You can answer the question, the old age question that you always wanted to know: how much caffeine is in a tea bag, and is it really what they're telling me it is, right? And finally, we have the waste and chemicals disposal. Think about the chemicals that you use today, especially, for example, the base that you use today. What was the base that you used, and where can you dispose of it? Was it solid? Was it liquid? And that's pretty much it. Thank you for listening, and I hope you learned something today. Bye-bye.